Okay, so here we go. Sorry for the late start. I lost track of time. It's as simple as that. Okay, so last time we were talking about vector line integrals. Okay, we do need to get started. Last time we were talking about vector line integrals. What I want to do now is... are we good? Okay. I want to talk about a different point of view on vector line integrals. So vector line integrals, so far, we've talked about them as representing work. And that is in a specific context where the vector field represents forces. And then if you look at what we're looking at here, we've got force dot displacement, and of course that gives you work. Okay, so here's the thing. What would happen if all of a sudden our vector field represents a fluid flow? What then would this mean? It's not going to be work, right? It's pretty clearly not work. Well, what does velocity dot displacement mean? And it's not anything that we particularly recognize, right? So we're going to have to do some work to figure out, no pun intended, to figure out what actually this is talking about, right? In this context where a vector field represents a fluid flow, what do line integrals represent? The way I'm going to get to this is by asking a seemingly out-of-the-blue question, right? And with this out-of-the-blue question asked, by the way, all of this is just kind of a repetition. Sometimes I like to be able to come up and make references to the picture. There's nothing new in this section. The out-of-the-blue question, it's going to turn out that the answer will have something to do with vector line integrals. And being able to make the connection from that question to line integrals being part of the answer, we're going to be able to make a reasonable interpretation. So here's the question, and I emphasize this is out of the blue, right? It's kind of a weird thing. Usually when you're doing something, some sort of an application, you start with, hey, here's a physical quantity that I already understand, and I just want to compute it. And that's not what's going to happen here. I'm going to describe some just strange, seemingly out of the blue, unmotivated quantity. Okay, so here it is. Suppose we have a curve, right, like this. And suppose we have a fluid flowing around it. That's what our vector field represents. And then further, let's look at the amount of fluid that's in this kind of tube-like shape here, something like this. This being what you get when you take a cross-sectional area A here and kind of drag it across the curve like that. All right, there's a strange little construction. So we've got all this yellow region in which there's fluid, and we want to ask the question, again, random, weird, seemingly out of nowhere, but grand total over all of this yellow fluid. To what extent do we feel like the fluid is flowing along the curve? That's the question we're interested in. To what extent is this fluid, all of it, flowing along the curve? Again, weird. Why do we care, right? But valid. Seems to come out of nowhere. Okay, so the way we're going to get at this is by breaking it up into little pieces. So in particular, instead of looking at all of the fluid, I'm going to look at one little piece of the fluid. Like this, right? Teeny tiny little piece of fluid. This corresponding to the part of the curve of length ds, some little bitty piece of curve. So there's a little piece of fluid. Now the fluid is flowing. The fluid has some velocity, something like that, right? But again, we're not interested in how the fluid is flowing overall. We're interested in how the fluid, to what extent is the fluid flowing along the curve. So along the curve, all we care about then is its component in the direction the curve is going. Its component, in other words, in the tangent vector direction, the t direction. Okay, so this is what we're actually interested in. And so for, the extent to which we have an answer to this question, at least as pertains to that little bitty piece of fluid, well, it's a simple matter of the component, which of course is just a dot product, right? Dot product with the unit vector, times, well, how much fluid are we talking about? Which, of course, is volume, which, of course, is area times thickness. Right? So, I mean, that's just sort of a direct take, anyway, on a partial answer to this question. Fluid, here it is, ADS, flowing along the curve, there's that F dot T. Okay, so now that is, of course, just the DQ. This is not the This is not the total answer. The total answer that I'm interested in is going to be an integral of that. I've got to add this up over all of these little small pieces of the curve. And take this formula, plug it in for DQ, which is, I guess I will do like this, kind of like that, and then move things around as appropriate. And what you notice pretty quickly is that a line integral is part of the answer. So let's see here, looking at, again, this total question. Right, we know grand total extent to which the fluid is flowing along the curve, this quantity, this grand total here, and you see how the line integral has showed up. The line integral relates to whatever this weird question is. Okay, now in order to give an answer, in order to be able to phrase an answer, so again, how do I interpret this vector line integral? I am going to try to get rid of this business with area here, and so I'm going to make the observation that looking at the picture, well, I mean, the bigger the area, the more the fluid. I mean, that's sort of obvious. It's just directly proportional to area. So that not being the part of the answer that I'm really interested in, I'm gonna say, look, of course this is per unit area. Of course more area gives you more flow along the curve because it gives you more fluid to be flowing. So I'm going to phrase it as per unit area, but the answer then is, aside from this area, this line integral is telling you how much the fluid is flowing along the curve. Again, per unit area. So this is an answer of a sort to our question, our original question. What does a vector line integral mean? What do I mean by an integral along a curve of a vector field if that vector field represents a fluid flow? Well, strange though it seems, it's telling you how much the fluid is flowing along the curve in some sense. Okay. How are we doing? Everybody with me? Okay. All right. So there's a particular special case of this that we care about. It's this vector line integral. It's called circulation in the following special case. The special case is that the curve over which you're computing it is a closed curve. So you can compute a vector line integral over any curve, but in the special case where you're talking about a closed curve, such as this one here that starts, let's say, at that point and then goes around and then ends exactly at the same point. When you're talking about circulation around that closed curve, we call it circulation. I think I actually said it before I should have. Anyway, so line integral, closed curve, circulation. Okay, that's just a little bit of terminology. Now let me try to kind of motivate the terminology. I'm going to think through an example first. Let's look at this example where we have this closed curve like that. Here is our vector field, like so, et cetera, all the way around. And let's just think through what would the line integral be if I were to add up over this blue curve. And, well, let's see here. Along in this part of the curve, the curve is going that way. The fluid is going the same way, right? So the fluid is flowing very significantly along the curve, along in here. And then likewise, over here, same deal. Fluid's flowing literally very much along the curve. Same here, and yada, 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 all the way around this curve. And so grand total, what I would expect of this line integral, aka this circulation in this case, I would expect that circulation to be positive because I'm getting positive contributions each little way along the curve. Does that make sense? Okay. All right. So before I go to these other examples, let me point out this actually gives me a point of view on why we use the term circulation. So let's think about what the curve does. Forget about the fluid for a moment. The curve itself goes around in kind of a circle. Now that's not really quite the point, but certainly the tangent vector. If I were to look just at the tangent vector, forget about where I am on the curve, but just looking at the tangent vector itself, the tangent vector literally goes around in a circle. All right, it starts pointing up, it points in all the directions, and it ends pointing up. Does that make sense to everybody? Okay. Now, again, the integral is computing the extent to which the fluid is kind of following along the curve. So, said differently, this thing, circulation, is measuring the extent to which the fluid is also kind of going around in a circle of sorts, that its direction anyway is going around in a circle. Because it's literally measuring the extent to which it's following the curve, and the curve is going around in a circle. So that's the motivation, anyway, for this term circulation. It's a pretty reasonable choice, I think. Now let's see another example. Going back to the same vector field, but let's look at it in this other context. So here, same vector field. But now we're going to look at this curve going the opposite way. Same underlying curve, clockwise instead of counterclockwise. Now again, one little piece at a time. Let's look, along this little piece of curve right here. Well, I mean, look, the curve is going this way. The fluid is going that way. And so to what extent is the fluid doing what the curve is doing? Well, it's doing the opposite of what the curve is doing. We would expect this dot product, vector field dot dx, and the dx, of course, is pointing in the direction that the blue curve is going. We would expect this to be negative, at least along that part of the curve. And again, adding up over the entire curve, you look here, color. You look here, you look here, you look there, the whole way around. In this case, we're getting negative contributions the whole way around. So again, here I would expect the circulation, that vector line integral, to be negative. Everybody all right? Okay. All right. Now, sometimes it's just not that simple. Here's a scenario that really is kind of hard to tell. I've got a closed curve that I have in blue here, and again I've got the same vector field, exact same vector field. What you're going to notice though is that in some places the vector field is going, let's see here, the curve is going that way, right, as I have it drawn. So in some places the fluid is going opposite of the direction that the curve is going. In other places, the same vector field is going positively in the same direction that the curve is going. So in some places I'm going to get negative terms, in some places I'm going to get positive terms. And as I add up over this entire curve, it's not immediately obvious whether there's more positive or whether there's more negative. Right? So in this case, it's I'm just going to leave it as a question mark. We can't really tell. It's not always as conveniently obvious as it is in cases like that. Sometimes you have to compute directly, and there's some fancy tricks that we're going to talk about. We're going to actually kind of start talking about the fancy tricks later today. We probably won't quite get there. But certainly by the end of this week, we'll have some clever tools for analyzing this. Okay. All righty. Last thing I want to talk about is how to sort of visualize, what this means geometrically. This is a subtle idea, but I'm just going to make a hand-waving geometric appeal. If you have a small object, and I'm not going to be precise about what I mean by small. Loosely speaking, what I mean by small is small enough that there's just kind of a consistency. There's not enough room for things to change particularly dramatically. Right? Not that they're constant, but that things just don't change very much. So when you have a small object, and let's imagine that this here is a small object. I like to think of this, for example, as being a leaf. Fall colors, right? So leaf falls off of a tree and it lands in a creek, and it flows downstream, right? But it might not just flow straight downstream. It might, as it goes, it might actually have a rotational aspect to it. You've probably seen this as things kind of float downstream. They can be kind of rotating as they flow, right? So this dead leaf, which way would it be rotating as it goes downstream? And I would point out in this case, if this is the nature of the fluid, if this is literally the water around the going around the leaf, I would propose that this leaf would be turning counterclockwise, right? Now, why would it be going counterclockwise? Well, partly because there's water kind of pushing on the sort of the outside part of the leaf as it goes. The water is kind of pushing this way on this side and that way on that side. Now, to be fair, there's also stuff that's happening underneath the leaf. Yeah, sure. And here's where I'm going to invoke that the leaf is small and there's kind of a general consistency of a sort that we'll be able to make more precise a little bit later. But loosely speaking, this being small, the fact that this circulation here is positive means that we're getting an indication that the fluid is making this rotate the same direction that the curve is going. And of course, the curve is going, as I have it drawn here, counterclockwise. That means that this leaf, we would kind of expect it to rotate counterclockwise. Is that cool? Everybody happy? By the way, flashbacks to chapter 3. You may recall we've already talked about how things are rotated by fluid flowing around it, right? And at that time we were talking about curl. And at that time it was a three-dimensional context instead of a two-dimensional context. So this is kind of smacking of that chapter 3 discussion, but in a little bit of a different way. All right. Okay, how are we doing? Pausing. Questions? Everybody all right? Yeah, sorry.
So, for one of the homework problems that is assigned for 6.1, it has something that looks similar to the one where you said the circulation, like you didn't really know, but we you said we're going to learn how to do that in, I think, the next section. So I was wondering what the method to do that problem now would be.
I don't remember the problem.
I'll show you after.
Yeah. After
okay.
that'd be great. Yeah. I'm sure we'll be able to straighten it out. Yeah. Okay. All right. Okay. So moving along. There are a couple little bits that I need to mention before we go on to the next thing. One is always head on a swivel. Look for convenient, lucky breaks. I've made no secret that I'm a huge fan of symmetry theorems, right? And that's a big lucky break that you can take advantage of powerfully in many occasions. And again, my undergraduate experience, it was a big help. Massive, huge help. And a little bit less, but still also massively useful. It's what I'm going to call fortunate geometry. So let's just see case in point. And what I've got here is a curve that's parametrized like so. Now that's a weird parameterization you're going to notice. I haven't given you x, y, z. I've given you rho, phi, theta. So x, y, z is going to be worse. Right? After all, x is rho sine of phi u. Right? So I get sine of this, and then cosine of theta. So cosine of all this ugliness. That formula for x is horrifying. Right? And then likewise the formula for y, and maybe not so much the formula for z, but still pretty bad. And so this is a nightmarish curve that I've got parameterized here. And here's an attempt to draw, hypothetically, what that curve might look like. It's probably not very realistic, I wouldn't think. Here's the thing, though. Notice this curve has rho equal to 1, which means this entire curve is on the surface of the sphere. And the curve being on the surface of the sphere means that my dx vector, the tangent vector to this curve, is always going to be parallel to the sphere. Now that's just a geometric observation. Exactly what direction does dx point? Oh, I don't know. Well, that's details that would have to get worked out. But it is unavoidably going to have to be tangent to the sphere. Yes?
Is it because rho is constant?
That's right. In this case, because it's constant at 1. But yeah, the mere fact that it's constant is what makes the entire curve confined to a sphere centered at the origin, no less. Yeah. Right. Okay, so that's one observation. Dx is always tangent to the sphere. Let me kind of erase all the rest of that. Okay, now let's look at the vector field. The vector field, you'll notice, has a factor in it, which is the position vector. The position vector comes out of the origin. Of course, that's how we draw it. The vector field itself is a multiple of that, scalar multiple. Now, it's a weird scalar multiple, but nevertheless just a scalar. It's a highly non-constant scalar, but still a scalar. So whatever that factor is, that's a separate question, but the field vector always has to be parallel to the position vector. And if you think about it, now again, I love spheres. Position vectors on spheres centered at the origin, and this is exclusive to spheres centered at the origin, position vectors are always perpendicular to the surface. Right? Which means that our vector field is always perpendicular to that sphere surface. So now again, let's kind of get rid of our all the distractions. What we really need now is keep in mind, we're looking at f dot dx, looking at the dot product. Right? If you're looking inside of an integral, you can see right there f dot dx. So what can I say about f dot dx? Maybe 2 seconds. F dot dx, well, f and dx, one of them is parallel, one of them is perpendicular. Therefore, the dot product is 0, and therefore this line integral is 0. Yeah, question?
Sorry, do you mind explaining again why dx is always parallel to the sphere?
Yeah, because you're moving on the surface of the sphere, and when you're moving on a surface, your velocity is always tangent to the surface. It's just it's a geometric appeal, right? If I'm imagine this tabletop here. It's chalk everywhere. Good Lord. If some ant was walking on this table surface, his velocity would always be parallel to the surface. Right? An ant walking on this can't have a velocity that's up. Does that make sense? Yeah. Yes.
How do you know that f is always perpendicular?
Yeah, right. So f is always parallel to the position vector, and now I'm just going to make a geometric appeal about spheres, specifically spheres centered at the origin. The position vector being kind of a radius, if you will, of the sphere, always perpendicular to the sphere. And the vector, the field vector being parallel to that radius, also perpendicular to the sphere. Yeah. So, neat fact. Now, you get lucky sometimes. Where do I credit this good fortune, this geometric good fortune? And it's the sphere. It's the fact that we identified from the statement of the question here that we're on a wonderful surface, namely a sphere. Even better, a sphere centered at the origin, right? And it just has these wonderful geometric symmetries, namely, so for example, about radii being perpendicular to the surface. You don't get that with any other surface. So be on the lookout for this kind of good fortune, right? If you're doing business on a sphere, just keep your eyes open. It's possible there might be some good luck in there somewhere. And this comes up a lot. And y'all can look at my old exams, and there's plenty of examples of lucky breaks that I've deliberately put in there for students to take advantage of. Yeah.
So in the picture, the x vector acts as the radius, so therefore dx is perpendicular to it.
Yep. And that's just the nature of spheres.
Okay.
Yep. All right. Okay. So let's see here. Next, this is largely a cultural thing, and it's stuff that's kind of got to get said. We know from long ago that we have this thing called dx. That, among other things, we know is x prime dt. So I'm just going to make the observation, look, you could just write that out in coordinates. And you could multiply that out by coordinates. And then you can recognize one coordinate at a time, x prime dt is dx. Likewise dy, likewise dz, right? So it seems a little weird to want to do this, but nevertheless perfectly reasonable to rewrite dx vector in coordinates. All right. Well, likewise, we can write our vector field, f, in coordinates. So we can have some coordinates. Let's call them PQR, which is weird but standard. And so here's the thing. If f is PQR, and if the dx vector is dx, dy, dz. Now look at our little piece of our vector line integral. I can view that as being a dot product of vectors whose coordinates I can see. And you could just straight up just write out that dot product. And it's like this. Right? So again, weird. Who'd want to do this? What's to be gained from this? Why is this a good thing? How does this help me? In fact, let me complain about this before I say good things about it. What I have here is an alternative notation for vector line integrals, for which I already have a really good notation. And this notation here is what I like to call natural. F is a natural thing. It's a vector field. Maybe it represents velocity. Maybe it represents force, but it represents something physically natural. The dx vector, again, geometrically natural. It represents displacement. That's a real thing. You can draw a picture of it. It's meaningful to the context. Well, let's look at this over here. Well, what is q? It's kind of arbitrary in a way. It's the second coordinate of our vector field, so maybe it's the y coordinate of the force, but if you think about it, which coordinate it is depends on how you set up your bases. It's kind of arbitrary. Right? It's not really, by itself, it's not really that natural of a thing in your problem. So the way I view it, you look at these notations, and by the way, I'm going to, the statement that I make momentarily is to be understood just in the context of Math219. This seems to be merely clunkier and less natural as a notational alternative. So why would anyone ever do this? Right? Okay. So now let me say good things about it. It does turn out to be a really powerful idea in more advanced discussions of this kind of material. This is kind of like what differential forms look like. Differential forms are a super powerful idea. The big theorems that we're going to be proving later in Chapter 6 and in much of Chapter 7, really, really strong conclusions about those results can be kind of unified by way of this idea called differential forms. It's really, really important, really, really powerful. And frankly, differential forms, they kind of look sort of like this. right? So there are great reasons to want to do this. I just emphasize, though, those great reasons are not going to come up in this course, right? Okay, well, why am I wasting your time then with stuff that you're not going to see in this course? Well, the thing is, because of these great reasons, this notation is in common use. And one could quibble with whether or not the people that use this notation, are they really taking advantage of the powerful tools that this notation gives them? Maybe they are, maybe they're not. I've seen a little of both, right? But the thing is, for whatever reason, you're going to see this notation. This notation's out there. And that's why I have to show this to you. You're going to find it in your future. So what I encourage you to do is any time that you find yourself looking at this notation right here, to just remind yourself where it comes from. Remind yourself that the P, the Q, and the R are just telling you what your vector field is. And the dx and the dy and the dz are just a sort of expanded representation of the dx vector. And therefore, that this integral that you, again, will probably encounter at some point in your future is just a clunky way to say vector line integral. That's all it is. Just a notational alternative for vector line integral. And I myself, whenever I see this, the very first thing that I do is I rewrite it like this, and then I do business with the language that I find much more convenient and natural. Yeah?
If you were to try to use that, would you have to break it up into 3 separate integrals and evaluate?
Yeah. Which, if you get right down to, look, when it comes to actually plugging and chugging, it's the same. It's literally the same, because, this right here, you're going to have to do that dot product anyway. The algebra is ultimately identical. It's just a question of how do you represent that algebra. And I find this much easier to deal with, much easier to understand. And I find this to be, mathematically powerful in abstract ways that I tend not to have a use for in a real-world scenario. Does that make sense?
Yeah.
Is everybody happy with that? Okay. All right. Okie dokie. So that had to get said. Last thing before we go on, symmetry theorems. Good news. We like symmetry theorems. Symmetry theorems turn otherwise very difficult problems into a snap of a finger. Yeah, you got to think through some details, right? But way easier in many, many, many cases. There is an odd symmetry theorem for scalar line integrals. Gotta love it. Notice I've written down this theorem deliberately, laying out on the page in the way to emphasize that it looks exactly like the odd symmetry theorem that we wrote down for double integrals, the odd symmetry theorem we wrote down for triple integrals. It's morally equivalent. And it's got the same warnings. Make sure that you check both conditions. You got to have both conditions for it to work. Make sure that you use the same line for each of these two conditions. It does have to be the same line. So it's just like all these other symmetry theorems, it's delicate. You got to check everything. If anything goes wrong, you're left with nothing, right? So careful, right? But really very, very similar. And very nice. Enjoy. Hope you find this useful. There is one difference. It's a warning. It's yet another little additional landmine that you have to worry about not stepping on, and that is keyword here, scalar. This only works for scalar line integrals. It absolutely does not work for vector line integrals. So for vector line integrals, you cannot have an odd symmetry theorem. Now, let me just try to give you some reasonable sense for why this would be, and keep in mind when I say odd, first of all, when I say vector line integral, we're talking about this. And when I say odd, let's see, I'll do this. Odd, I'm talking about the integrand, namely the vector field, right? So this is what, if it were odd, I claim would not be enough information to draw any good conclusions. The reason why, now let's take this let's take this expression and rewrite it. I'm going to take this point of view on the vector line integral, because here I can explicitly see my ds on each side of the reflection. Right? Here you'll notice I have a curve here that's symmetric over a line of reflection and blah, blah. So we have that the ds, as it's supposed to be, is the same on both sides. But now look at these t vectors, and the t vectors just aren't. This t vector is that way. This t vector is that way. They're not the same. So the fact that your vector field is odd, right? Keep in mind, odd symmetry would mean the vector field is odd. The fact that this behaves nicely, so what? This part doesn't. So it just doesn't work. So again, be super duper careful about that, right? Don't go around rewriting, making symmetry claims about vector line integrals. Correction, not odd symmetry claims about vector line integrals. Now, I'm going to confess there is a different version of the theorem, but frankly, it's pretty hard to state. It's a lot more trouble than it's worth. You don't want to go there, right? But what you will make use of and can make use of if you find yourself looking at a vector line integral like so, and you wish you could use a symmetry theorem, what you should do is rewrite it like this. Notice that is effectively a scalar line integral. You've got to look at f and t, right? And if f dot t, namely if you're integrand there, if that's odd, then you're good to go. Right? So short version, turn your vector line integral into a scalar line integral first, and if that works out, if that satisfies odd symmetry, then you're in business. Okay. Everybody happy? Okay. All righty. Okay, so that's 6.1. Going to move on to 6.2. There's a bunch of theorems that we're going to be developing. Big theorems, powerful theorems that we'll be developing over the next few weeks. What is it about? Is this week 10? No, this is week 11. I think this is week 11. My gosh. Over the next, including this week, 5 weeks, there's several theorems in chapter 6 and 7 that apply in different contexts that are geometrically different, but which are really analogous and seem to have a lot of the same earmarks and can be understood in analogous ways and are susceptible to various comparisons, very strong comparisons. They're basically kind of the same ideas over and over and over again. So what I'm going to be doing, the way I'm going to be presenting these theorems is with that analogy in mind, with these strong connections in mind. I'm not going to present Green's theorem in the way that makes it most immediate to understand if that's your only goal. I'm going to be presenting Green's theorem in a way that will help you see how Green's theorem and Stokes' theorem and Gauss's theorem and the fundamental theorem of line integrals and the other fundamental theorem of line integrals and the fundamental theorem of calculus are actually kind of all the same theorem. So that's going to be my motivation. There are various different ideas that play in with all of these. There's what do we mean by boundary? We're going to talk about that. There's what do I mean by an accumulating quantity, and what is the relevant one that we're going to talk about? And what do I mean by a density? So you're going to see that in all of the discussions I'm going to give of all of these theorems. So just to get the ball rolling, we will start here. It relates to Green's theorem. We're going to start by talking about what we mean by boundary. So here we go. Okay, so broad point. Henceforth, boundary means oriented. It hasn't up to now, right? Up to now, when I say boundary, it just means kind of where does my set end and where does not set begin, right? It's the edge, right? It's a curve. It just kind of sits there. for the purposes of doing what we need to do, I need for the idea of a boundary to be not just a thing, but an oriented thing, and specifically oriented according to certain conventions. Specifically, we're going to talk now about the convention in the context of Green's theorem. I want to emphasize this is arbitrary. Arbitrary does not mean irrelevant. Arbitrary, in this case, means that there is a standard that's been in place for 150 years-ish, maybe probably more, 175, something like that. Very, 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 very long time, and this is the standard that is and always has been the standard, and so it's just, we have to stick with it. Okay, so the arbitrary but standard convention on orientation goes like this. If you have a region, and I'm only drawing a part of the region D here, is that D is some big region, and I just want to focus on just one little part there. The boundary curve means exactly what you think it means. Right? So it goes on and on. But keep in mind that boundary is now an oriented thing, so I've got to describe what do I mean by the orientation. Which direction along this boundary does the orientation point? Does the orientation go like this, or does the orientation go like this? What's the right way to move along this boundary? Arbitrary but standard is that the orientation points in whichever direction, that when you go that way, the thing you're talking about the boundary of is on your left. That's a simple rule. Always go around the boundary in such a way that the region is on your left. Why left? Again, arbitrary. Somebody made this decision 175 years ago. It didn't matter then, but because they've made that decision, it really does matter now. This is the standard. Yes?
So you say is oriented such that he is on the left? Is saying oriented to say go travel the curve from left to right?
Yeah. It means travel the curve in the direction indicated by what we call the orientation vector. Okay. So remember, when we first started talking about vector line integrals some time ago, right? We made the realization that if you're computing work, it really matters which direction you go along the curve, right? So we invented this idea of an oriented curve, which is a curve that comes paired with an indication of which way you have to go. Does that make sense?
Yeah.
So that's what I mean by an orientation here. It's indicating which direction are we unavoidably going to have to go around that curve. Yeah. Yes?
But for subparts of the curve, wouldn't top and bottom make more sense?
Yeah. And that's why I drew this second picture here. So now let's look at this other, same region D, but now looking way up near the top, and up near the top, maybe it's, the boundary curve is going to be kind of maybe like this, and of course it goes on in both directions. But anyway, up there, which direction should I go? Should I go this way or this way? Well, we have to go in such a way that the region is on my left. And which one of these two different options would describe the direction that I should go in order for this to be my left? Well, if this is my left, then I'm unavoidably going that way, right? Because if I went this other way, the region would be on my right. Does that make sense?
So D is the black arrow. It's not the green.
Yeah, on the left, yeah, saying that the D, the solid whose boundary I'm talking about, saying that that's on the left, notice as I go in this direction here, right, imagine me walking that way, then the yellow region is on my left. Yeah. Is that cool? Arbitrary, but standard. Okay, now, good news. Most of the time, there's an even simpler rule for this. Let me just see if I can get all this at once. There we go. Even simpler rule. Notice that if you're talking about an outside boundary curve, like that, and your region being on the inside like that, well, the direction you go to have the region on your left, oh, that's terrible. Okay, there we go. The direction you would go to have the region on your left, always counterclockwise. Very handy. Okay. Now, this is not quite a universal thing. Boundary does not always mean counterclockwise. It only means counterclockwise if you're talking around the outside boundary. Notice if you're talking about a solid that has kind of inside boundary to it. So, for example, let's look at this region here like this. Sure, counterclockwise around the outside boundary, but clockwise around the inside boundary, because that is what has the region on my left. Right? That makes sense? All right. Okay. So, good news, most of the time we're talking about simply connected surfaces that don't have holes in them and like this, and then so it does, in practice, tend to be pretty straightforward that, counterclockwise most of the time. Okay, all right, now let's talk about what we mean by accumulation. Y'all have heard me talk about accumulation quite a bit. Right? Accumulation is at the heart of everything that we ever do with integrals. Right? Every integral is of a quantity where the whole is the sum of the parts. Mass. You can compute mass with an integral because you can take your mass, you can chop up your mass into little pieces, and the whole mass is the sum of the little pieces of mass. So mass accumulates over areas, and from a triple integrals point of view, mass accumulates over volumes. Likewise, population, likewise, various other things that we've computed. Okay. All right. Now, I want to point out, not every quantity that you might ever be interested in is an accumulating quantity. So, in particular, talking about areas, right? So, for example, here is an area, and I can talk about chopping this up into two different pieces. For example, there's this left piece that I'm going to kind of pseudo shade blue, and there's this right piece that I'm going to pseudo shade orange. All right, so the mass in the green is equal to the mass in the blue plus the mass in the orange, sure. But notice perimeter doesn't work. The perimeter of that green region is not the same as the perimeter of the blue plus the perimeter of the orange, is it? It's just not, right? There's this extra piece in here that gets counted kind of twice. In fact, it's part of the boundary, part of the perimeter of the blue thing, it's part of the perimeter of the orange thing. It's not part of the perimeter of the green thing at all. So let's, as much as I like accumulation and using accumulation arguments, let's not lose our cool and just go around assuming that everything accumulates, right? But again, perimeter clearly doesn't. So that said, there is a particular thing, a particular accumulating quantity of interest that feels a lot like perimeter but isn't, and it's boundary circulation. This is very surprising. Actually that's fine. Boundary circulation is an accumulating quantity. So in particular, if I were to think about the boundary circulation for this hole, and if I were to look at the boundary circulation specifically just around the left side, and then the boundary circulation specifically only around the right side, I claim that these add up. I claim that the green boundary circulation is equal to the blue plus the orange boundary circulations. And now why would that be? Let me draw a more representative picture. Let's see here, the green boundary circulation is there. That's the boundary of the green, right? Now let's see here, the blue boundary circulation would be like that. plus that. And then the orange boundary circulation would be like, well, that plus that. Now it's tempting to say, okay, well, clearly these track and cancel from opposite sides of the equation, so that's not a problem. Likewise, all of this, right, orange and green, they track. They're the same in the orange as they are in the green, so that cancels. And then again, we get a leftover. And it's tempting to say, look, this leftover represents the difference. This leftover represents why boundary circulation doesn't seem to accumulate. But check it out. This is all over the same curve. Both of these little pieces are over the same red curve, except with opposite orientations. So they cancel, and there's nothing left. So weirdly, boundary circulation actually is an accumulating quantity. Again, specifically accumulating over areas. Everybody buy it? Everybody okay? By the way, I forget, am I out of time? I'm probably out of time. Let's see, 2:32. Were we supposed to end at 2:30?
Yeah.
I'm sorry. Okay, so calling it here, and y'all have a good day. See you later.